Dear students, now we are going to think about analyzing frames using the strain energy and consistent deformation method. So to analyze frames, we need to have clear picture of a concept called as transformation of forces. That is how to transform the force from one point to another point in a given structure. So I'm calling it as transformation of forces. It's a very simple concept, and for this you just require the understanding of basic equations of equilibrium that you learn from engineering mechanics. Okay, so let's see what it is. So when I say transformation of forces, I'm considering a cantilever beam. Okay, so that this concept will be clear for you. I'm using a cantilever beam. Okay, this is the cantilever beam what I'm having, and it is subjected to some kind of loading. Let there be a load Fx in the x direction, Fy in the y direction at the free end. Okay, so that's the loading condition. I'm considering this as positive x, this as positive y, so that's a sign convention. Now we have different points, so we should have names for the different points. So let this be point A, this be point B, and this be point C. And I'm giving some length also. Let this member is having a length L, and this is also having a length L. So this is the basic condition what I'm assuming. Now what I'm going to check is, I'm going to check the free body diagram of the element BC. Okay, we are all very familiar with free body diagram. So I'm plotting the free body diagram of BC. So how will it look? I'll be having a member like this, which is basically my BC. This is point B, this is point C, and the forces Fx and Fy are acting here. And we know that if a system is in equilibrium, each and every part of the system will also be in equilibrium. That is the basic concept we are going to use here. That is, if a system is in equilibrium, every part, the system ABC is in equilibrium under the action of these forces, which means that the part BC and part AB, everything will be in equilibrium. So now I have BC. So now I need to think about the forces in here. And what is the function of these forces? These forces will try to maintain equilibrium of this particular member BC. Now from the very first module of SA1, you have seen the cases of trusses, method of section you have learned. So if you have a truss member, okay, let this be a truss member, and in a truss member, if you are taking a section, what happens? If I'm taking a section in a truss member, we will represent these as forces. Okay, we'll be representing these as forces. If I cut a section at this particular point, I will be representing this member and this member as forces. And this is the case when the force, nature of force is compression. So you already have the sign convention. This is compression, and if it is tension, this is the sign convention that we normally adopt. Okay, so when you are cutting a truss member, you will be getting a axial force, which will be either compression or tension. But if you cut a beam, that is a beam element or a frame element, okay, a part of a frame or part of a beam, what are the forces you are going to get? That's what we are really interested in this particular case. So when we cut a frame member, we are going to get three forces. If it's a 2D frame, we are going to get three forces. One is a force, that is a reaction, horizontal reaction. We'll be getting a vertical reaction, and we will be getting a moment. Okay, when we cut a beam or a frame member, these are the forces we are going to get. So I'm giving some names here also. Let this point is B, so let this be RB, HB, and MB. Okay, now we know that this system is in equilibrium, so this part is in equilibrium. So I'm going to apply the different equations of equilibrium for this particular beam. So first I am trying with sigma fx equal to 0. So we have already defined x direction. So what about the here? There is an HB acting to the right, Fx acting to the right, positive is to the right. So HB plus Fx equal to 0, from which I will be getting the value of HB as minus Fx. Now I am trying sigma Fy equal to 0. So what will I get? Upward is the positive direction. So RB is upward. RB plus Fy equal to 0, from which I will get the value of RB as minus Fy. Now, if this is in equilibrium, it should satisfy the third condition also, right? What is the third condition? Sigma m should be 0. Okay, I'm trying that also. So I'm taking this point, sigma mp equal to 0. And again, I'm repeating, whenever we write summation of moment, the sign convention is clockwise, anti-clockwise. So mb is clockwise. Okay, so I'm putting it as positive. And what is the other forces that is creating moment at point B? RB is passing through point, so lever arm is 0, moment contribution is 0. HB passing through the point, moment contribution is 0. Fx is also passing through the point, the line of action is passing through the point, so the contribution of Fx is also 0, but Fy will contribute. Okay, we have this length as L from the earlier assumption. So Fy times L is the moment caused by, okay, Fy times L is the moment caused by the force Fy at point B. And you can see here, if I apply a force like this, it is going to rotate in the anti-clockwise direction, which means minus Fy times L equal to 0, excuse me, which will give the value of MB as Fyl. Okay, so now we have all the forces or the reactions when I cut a section at point B. So I have the magnitudes and direction of all these reactions. So now this BC beam is in equilibrium. So what are basically these things? We know that these are RA, HB, MB, these are all reactions, right? What is causing this reaction in this beam? These are the reactions produced by the part AB, right? When I'm trying to pull this part BC, okay, when I'm trying to pull the part BC, what happens? When I'm trying to pull this part AB is going to resist. Okay, so whatever I got are the reactions exerted by AB. So Fx is to the right, so it is trying to pull to the right. So what will AB do? AB will pull it in the other direction, the opposite direction. Fx is to the right, so this reaction offered by AB is to the left. That's what we got here. We got the reaction offered by the portion AB as minus Fx, that is to the left. So these are the reactions offered by AB. Okay, I can call these as reactions offered or exerted by AB. If these are the reactions, what will be the actions on AB? Right? If these are the reactions exerted by AB, what will be the actions on AB? We can think about that also. So I'm trying to plot the free body diagram of AB. So I'm keeping it as fixed, or else I need to show the reaction. So instead of that, I'm putting it like this. So what will be the reactions? Sorry, what will be the actions? These are the reactions. So actions will be, from Newton's third law, we know that every action has got an equal and opposite reaction, right? So here you can see the reaction at this point is to the right minus Fx, which means it is basically Fx to the left. Okay, I'm taking this point. So what I'm having is, if I pull this here, it is going to have a reaction in this direction. So reaction is to the left minus Fx. So what will be the action at this point? It will be Fx, right? HP is minus Fx. So this is going to be plus Fx. Similarly, RB, I got it as minus Fy. So here it's going to be plus Fy. Now the moment I got it as Fyl positive in this direction, so what I'm going to get is a minus Fyl. I assumed it in this direction. Okay, if I'm putting it like this itself, then it's going to be minus Fyl. Okay, or else I can replace this this is clockwise. If I'm putting this arrow, the direction as anti-clockwise, it will be plus FYL. So if I want to plot the portion AB, the portion AB can be represented like this: A and B, okay, they're having length L, and the values of forces are Fx, Fy, and this is clockwise minus Fy, which means anti-clockwise FYL. So what I did here is I transformed the forces Fx and Fy acting at C to the point B, and what I'm going to get are these values. So even though there were just 2 point forces or two forces acting at this point, when I transformed this to point B, I was having a moment also, so that this part will be in equilibrium. So you should be very careful whenever you transform force. You should ensure that these 3 conditions are met, because if a system is in equilibrium, every part of the system is in equilibrium. So based on this concept, we'll be transferring forces at one point in a system to forces in another point in a system. Okay, in case of beams, this is not much relevant. We can do it without thinking about all this. But when it comes to frames, this is a very highly relevant topic. Only if we have the clear concept of this, we can proceed further. So we are going to consider a case of a simple frame. Okay, so I'm going to apply that concept here. So I have a frame. Let's consider I have a frame like this. Let this end be fixed. Okay, and it is subjected to a point load, say Fx, and a load like this Fy, and I'm giving some values. Let it be L, L, and L by 2, and let the EI value be constant. Okay, this EI is not a matter when we are thinking about the force transformation, but still, to complete the figure, I'm using the value. Now I'm giving some names. Let this be point A, B, C, and D. Now what I want to do is I want to transfer these 2 forces Fx and Fy to different points, and I want to know what are going to be the effect. Okay, so first I'm going to transfer the forces to the point C. Okay, transforming the forces to point C. So let's see how to do it. So I'll be taking only this part. So this part I'm going to ignore. So I'm having a system like this. Okay, and the names are A, B, and C. Now I need to have these forces transformed here. So the easiest method is just consider this. So what we are doing is we are transforming all these here. So just put a section there. Okay, you can put it like this or you can put it like this, both are fine. Okay, so I'm considering a section like this at point C. Now what are the forces I'm seeing here? Here I have a force to the right. So automatically I can plot a force to the right, Fx. Okay, because what is effect? This frame is getting pulled in this direction. So if I consider this, it is also getting pulled with the same Fx. So this is the transformation of Fx. And if I take here, there is an Fy pulling it downward. So I'm also having Fy. Now what is the effect? Is there the earlier case we have seen that there can be a moment also. We need to be very careful. We should not ignore the moment component. So let's see what the moment component is. So when I consider a section at point C, there are 2 forces, right? This Fy is passing through the point C. The line of action of Fy is through C, so it cannot create any moment at all, right? Because the lever arm, if I'm considering point C, the lever arm for force Fy is 0. So the effect of Fy in contributing a moment is 0. But what about Fx? So if I consider this point, if I apply a load, it is going to create a moment like this, right? It's going to create a moment like this. So when I consider here, the moment caused by this Fx is going to be Fx times L by 2. Okay, Fx times L by 2, and its effect is a anti-clockwise moment. So you can directly plot it like this: Fx times L. Okay. So when you are transferring these two forces to point C, what you are going to get is something like this. Is that okay? Now, again, I'm not stopping here. I'm going to the transfer to point B. Okay. So point B, so what I'm having is just this. And the points are, this is point A and this is point B. Now what about here? So either I can refer this figure or I can refer this figure. Both are fine. Okay, we have transformed the forces from D to C. So you can move on and think about only this figure, or you can start from here. Both are going to give you the same results. So now let's see. Okay, so I'm trying from here because these two are creating the same effect. So I'm trying from here. So now I'm taking the section at B. So what is the effect? There is a force Fx to the right. So I'm putting it Fx to the right. Fy downward. Okay, I'm putting Fy downward. And what else? Now I need to think about the moment. So this Fx is passing through, the line of action of Fx is through B, so it cannot create any moment. Okay, it can only create a axial force, it cannot create moment. But Fy can create a moment. And what is the direction of the moment? It is clockwise. So now I'm going to think about the moment part. Okay, so this Fy is creating a clockwise moment. This lever arm is L, so Fy times L clockwise. So Fy times L clockwise. I have marked this as clockwise, so this is also clockwise. Then I have a moment Fx times L anti-clockwise. Here I marked it as clockwise, so anti-clockwise will be negative. Okay. Oh, I forgot. Here it should be L by 2 because this lever arm is L by 2. So Fx times L by 2 should be the value here. So here also Fx times L by 2. So now I have, okay, transformed these two forces to point B. And I did the transformation from this figure. What if I'm trying to transform it from this figure? We are going to get the same value. Let's see how to do it. So I'm taking the section at B. So there is a force Fx to the right, I mark that. Fy to the right, I mark that. Now I need to think about the moment value. So what are the moment? This Fy has got a lever arm of L, right? This is a force. So at this point, if I'm considering, say I'm considering like this Fy is acting like this. It is going to create a clockwise moment having magnitude Fy times L. Okay, Fy times L. Now what about this? What is the effect of this? So you can see here it is creating a anti-clockwise moment. I'm taking the point B again. Anti-clockwise moment Fx times the lever arm is L by 2. That is minus Fx times L by 2. I'm getting the same thing. So either I can come from this figure or I can come from this figure. I'm going to get the same result. Okay. Now I'm going for one more transfer. I'm going to transfer everything to point A. Okay. So now how will the figure be? So now what I'm going to do, I'm going to transfer everything to point A. Okay, sorry, I don't have to plot this. It's just this point, right? Just this point, which is point A. Now I can come from here. Okay, we have seen coming from here, here or here, everything is same. So I'm considering this point. So what is the effect? At this point, there is an Fy. Now what we are plotting, we need to be very clear about this concept. We are plotting the action figures. Okay, these are all the action figures. What do you mean by action figure? So if there is an action figure, there's going to be some reaction figures, right? So reaction figures are the reactions created at the supports, just like this. Here if you see, this is the action figure of point B and this is the reaction figure of point B. Okay, they will be just opposite to each other. Here you can see here this is a fixed support. So these are going to have reactions Ra, Ha and Ma. Those are the reactions. Now if I plot the figures in this way, what I'm going to get are the action figures, which are basically the forces acting on the system, and the reactions I will be getting from here. So I'm going to plot the actions here. So let's see what the actions are. So if I consider this point, okay, there is an Fy acting downward, okay. So I'm marking with this color all the actions and we'll see the reaction. So Fy, then there is an Fx, okay. And what about moment? This Fy times L, okay, this moment part I can directly take it here. So I'm plotting it like this, and what will be the value? The values I'm plotting here. So Fy times L minus Fx times L by 2, okay, I directly took it here. Now there is another component which is causing an additional moment. Fy cannot create any moment because it is the line of action is passing through A, but Fx, there is a lever arm of L and it is going to create a clockwise rotation, that is Fx times L, okay. I have marked it clockwise, so it is plus Fx times L, okay. This length is L, so Fx times L clockwise. So these are basically my action values, okay. So if I just this is minus Fxl by 2, this is plus Fxl, so this is going to become Fxl by 2 plus Fxl by 2. So I am going to get it as Fyl plus Fxl by 2. So that is the action value of moment. So now these three are the action values. Now if you want to plot the reactions of this particular support, what are the reaction values? Just reverse this. So here the action is Fy downward, so the reaction will be Fy upward. Fx to the right, which means Fx to the left. Then there is a moment, right? Moment is, I have marked it clockwise, so here it should be anti-clockwise, okay. I'm marking the moment as anti-clockwise, okay, anti-clockwise, and the value is Fyl plus Fxl by 2. So these are the reactions, and this is a determinate or indeterminate figure what we are discussing here. How many reactions will be there? At fixed end there are 3 reactions, at the free end there are no reactions at all. So this is basically a determinate structure. So I can try the equations of equilibrium to get the reaction values, right? If you use those equations, say I'm using the equation sigma Fy equal to 0, okay, these are the reactions. So what is the case? Fy upward, Fy downward, that is plus Fy minus Fy 0. Sigma Fx, Fx to the left, Fx to the right, 0. Now if I take about moment at this point, I'm again going to get the value as 0. So this is a system in equilibrium. So these are the action figures, and if you are having the action values, getting the reaction is just reversing the sign, you'll be getting the reactions. So this conversion or transformation of forces from one point to another point is going to take place when we try to solve an indeterminate structure using strain energy or consistent deformation method, because we want to get the expression for moment. For that, this is going to be a real help. So I want you to focus once more on how we transformed from this figure to this figure, because that is highly required. Okay, so from next video lecture onwards, we'll start analyzing indeterminate frames using strain energy method or consistent deformation method. Thank you.